Good afternoon. This video is probably going to be a little longer than usual because I'm trying to combine 3 topics into one video. They do all have to do with radicals. And the first section of this video is simplifying radical. A radical is simply a value that is in the form of rad of something, square root of something. For now, we'll just stay with square root. You can simplify cube roots. You can simplify fourth roots, of course. But while we're going over the basics of simplifying, we're going to stick with square roots. So unless I say different, every radical you see is a square root, not a cube root, not a fourth root. So as you know, x to the 1/2 power means square root of x. But since we're shifting into the world of radicals, you're not going to see, you're going to see this exponent less and less, and you're going to see more of this. After this video, you probably won't see that at all. I'm just going to stick with the radical sign. So first of all, we're going to start with this basic fact that square root of x squared equals x. And that may seem like common sense to you, but there is a reason. So why is that true? Well, if you go back to exponents, square root of x squared is the same thing as x squared raised to the 1/2 power. And you know that this is a power to a power, so I multiply the 2 powers and I get x to the first power, or just x. So this is why square root of x equals x. Now, it's also true that if I have the square root of a product, a times b, that square root of a, that equals square root of a times square root of b. This is another basic fact about radicals, which also may seem common sense, but there is a reason. In exponential form, square root of ab is ab to the 1/2 power. And this is power of a product, so I distribute that 1/2 exponent. And I get this, which in radical form is square root of a times square root of b. So you see, this is the proof. It is true that square root of ab equals square root of a times square root of b. And square root of x squared equals x. Okay, we're going to use these 2 facts a lot. Okay, so branching off of that, I can simplify more complicated things like square root of y squared, square root of x squared y squared. Now using this rule, I know I can chop this radical up into 2 radicals, product of 2 different radicals, square root of x squared times square root of y squared. And then once I've done that, I can take each one individually. I know from here that this equals x and this equals y. So that ends up being x times y, xy. Okay, now, but what if the exponent of x isn't 2? This fact I gave you was specific to the situation where the exponent of x is 2. What if it's 3? Well, I know what that means. It means x times x times x. And I know that this is x squared. And I know what to do with that. Square root of x squared there. So I'm going to rewrite this as square root of x squared times square root of x. And I know that becomes x. And this doesn't become anything else because I don't have another x in that rad to pair up with this x to make it x squared. Therefore, I can't simplify that radical any further, so this is as simple as this product gets. Square root of x cubed becomes x rad x. Okay? Every pair of x's in the rad becomes an x outside the rad. This x was a loner. There was no other x to pair with it, so it stays inside the rad. Okay, I have x and y again with different exponents, so I'm going to split it up just like I did last time. X to the fifth, rad, y to the fourth. And I'll write this out the long way, and the y's as well. And I just said that for every pair of x's, one x comes out of the rad. For every pair of x's in the rad, that transforms into an x outside the rad. So I have a pair here, gives me an x outside the rad. I have a pair here, gives me another x outside the rad. That x is going to stay inside the rad. So just put that x there. Now for the y's. Here's a pair of y's, so a y comes out. Here's a pair of y's, another y comes out, no y's left. And I'm just going to write this in exponential form so it looks nice and neat. And I end up with that. Now, do you have to do all these little micro steps? No. I'm doing this for those who've never seen anything like this before. You can, of course, you could probably skip this one if you can picture the 4 y's in your head. You may not need to write out the 4 y's. If you can picture the 5 x's like this, you may not have to write them out like this. Or if you can picture this and you don't even need to write that, maybe you can go straight from here to that. You need to gauge how comfortable you feel. If you feel shaky, do every step. If you feel very comfortable, no need to do every step. Okay, now I'm going to throw in a coefficient. 9x to the 6y to the 7th. So what do I do with this coefficient? Well, the coefficient is a base. It's a separate base. It's separate from x. It's separate from y. So I'm going to split this up into 3 rads, each with a different base, and simplify each rad separately. Square root of 9 happens to be a nice number. It's 3. Square root of x to the 6th happens to be x to the 3rd times x to the 3rd. Why am I writing it like that instead of 6 x's in a row? Because I have a pair. I have a pair of x cubed, so 1 x cubed will come out. And then the y's, I have y cubed, and an extra y. So I know that a y cubed will also come out, and I know that this y will stay inside. 3x cubed, y cubed, and there's a single y in the rad left over. And then one more example. Okay, I'm going to do this one a little differently. So I have 20, and I know that 20 is 4 times 5. So I know that since 4 is a perfect square, a 2 is going to come out because 4 is 2 squared. So a 2 will come out, and that 5 is not a perfect square, and it's prime, so it will stay inside. So I'll write the 5 there. Okay, now my x's, x to the 10th is x to the 5th times x to the 5th. So an x to the 5th will come out. And then my y's is y to the 7th times y to the 7th times y. So I know y to the 7th will come out, and this single y will stay. So I did this one differently just to show you there's another way of thinking about it. Perhaps you like this better, perhaps you don't, and then if you don't, maybe use this. Okay, if you want to pause it now and do some practice with simplifying radicals, if you've been assigned a worksheet or something like that, go on ahead. Okay, what I'm going to do now is go on to the second section of this video, multiplying radicals. Now, in the previous section, I showed you that square root of ab equals square root of a times square root of b. Well, I can flip that around also. I can say square root of a times square root of b equals square root of ab. So multiplying radicals like this simply gives you the product of the stuff that's inside in a new radical. This is multiplying radicals. So the foundation of multiplying radical is no different than what we were doing when we were simplifying radicals. When we were simplifying radicals, I told you to split up the factors and give each of them their own radical. When we're multiplying radicals, we're taking two or more different radicals that have to be multiplied, and we put the factors together in one bunch in one radical. And then after we put it in one radical, then we simplify it, if possible, if it's possible to simplify it further. So here's an example, rad 5 times negative 4 rad 20. The negative 4 is not in the rad, so I'll just copy that down. And then the two different rads have 5 and 20, so I am allowed to multiply the 5 and the 20 and put it all under one rad. And then, now I simplify this rad if it's possible to be simplified. And in this case, yes, of course it can be simplified, because square root of 100 is 10. So negative 40. Now there is another way we could have done this. Instead of combining the 5 and 20, getting 100 and putting it in one rad, I could have split up the 20 into 5 and 4 under inside rads. And then you see you have square root of 5 times square root of 5, which is just 5, times negative 4, times rad 4. Oh yeah, and then this is 2. So 5 times negative 4 times 2, which is negative 40. Okay, so there are several ways you could get to the answer, especially with rads. There are a lot of flexibility when dealing with radicals. Okay, here's another one. I'm going to first combine what's in the rads under one rad. But I'm not going to multiply the 18 and 3, I'm just going to leave it as 18 times 3. And then x squared, and then another x squared. Okay, first I see a pair of x squareds, so I know an x squared is coming out. Okay, now my 18 and 3 I'm going to, whoops, that should be a rad. I'm going to rewrite the 18 as 6 times 3 because I already had a 3 here, and now I see I have a pair of 3's. So a 3 will come out, get multiplied with this 4, and that 6 is going to stay. Okay, and one more example with multiplying radicals. Distributive property. This is in the form of A times B plus C. And we all know that you can distribute that A to the B and the C. So that's what I'm going to do. 2 rad 5 times rad 6. I'm going to write this on the side now. 2 rad 5 times rad 6. This is what I'm doing. And I'm allowed to put the 5 and the times 6 under 1 rad, 2 rad 30. So this times this is 2 rad 30. And then plus 2 rad 5 times 2. Okay, that 2 is not under the rad, so I may not multiply it with the 5, but I may multiply the 2 with the 2 here, because that's not under the rad either. So the product is 4 rad 5. And that's all you do, because we're just using distributive property. Okay, if you're ready to do some practice with multiplying radicals, if you've been given an assignment, then you can pause right here and go ahead and do that. Okay, we are now dividing radicals. When you are dividing radicals, you are allowed to put this whole fraction under one radical. Or, if you have a fraction inside one radical, you may chop it up into 2 radicals, one in the numerator and one in the denominator, if it helps. Why is this true? Well, if I start with this, this is the same thing as x over y to the 1/2 power. And I may write this as x times 1 over y to the 1/2 power by definition of division. And then power of a product, I may write this as x to the 1/2 times 1 over y to the 1/2. And then I may write this in radical form, rad x times 1 over rad y, and then write it as rad x over rad y. So this is the reason you're allowed to do that. And so the significance of this is, I think, a good illustration of it would be in rad 24 over rad 6. So I'm allowed to, by this rule, I'm allowed to write this as rad of 24 over 6. And 20 over 6 we all know is 4. And square root of 4 happens to be 2. So by putting the entire fraction under 1 rad, it gives me the ability to reduce it, to simplify that fraction. But now, since I know that, I also know I could just simplify the fraction from the beginning. So I don't necessarily have to do this. I could go straight from here to there, because I know I can put the 24 in the top and the 6 in the bottom of a single fraction and put that entire fraction under the rad. It'll end up being this anyway. And if I throw some variables in there, okay, so I'm not going to write one fraction under a rad. I'm just going to assume you understand that we can do that. I'm just going to cancel right now. So I know 32 over 8 is 4, so that becomes 4. And I know that here I'm supposed to subtract the exponents. So I get x to the 6th. Everything in the denominator has been canceled, so there's no more denominator. In the top, I have 4x to the 6th. Square root of 4 is 2, and the square root of x to the 6th is x cubed. Okay, if you need to do a little practice with the dividing, if you have some problems to do, you can pause it now before I talk about rationalizing denominators. Okay. Now there are going to be times when after simplifying a fraction or dividing radicals, you will be left with a radical in the denominator that cannot be simplified further. 2 is not a perfect square. There's no other 2 in the rad also. So nothing's going to come outside of this rad. This radical is done. It's done being simplified. Whatever it was before, it's done. However, this is not a suitable answer because we are not allowed to have radicals in the denominator. If we have any radicals in the denominator, we have to keep going. We have to keep going a couple steps to get rid of that radical in the denominator. Okay, so there's something we have to do to this fraction to make that denominator non-radical, not irrational. A rad of some number that's not a perfect square is called an irrational number. It is not rational. We want that denominator to be rational, to be an integer or some fraction like 2/3. We just don't want it to be a radical. So I'm going to use the fact that rad x times rad x equals x to do this. Rad x times rad x equals x. So if I multiply the denominator with the rad 2, then my new denominator will be 2. No more rad in the denominator. But I can't just go around multiplying all the denominators with rad 2. That would be cheating. I have to multiply this fraction by something that doesn't change the value of the fraction, meaning the number 1. So I have to multiply the top also with rad 2 to make this legal. So I am in effect multiplying this fraction by 1 in the form of rad 2 over rad 2 to get rid of that rad 2 in the denominator. The top will have a radical, but that's okay. I only said no radicals in the denominator. I didn't say anything about the numerator. You are allowed to have radicals in the numerator, just not the denominator. And in class I'll explain why this difference is so important. So let's try that again. If I have 5 over rad 6, I can't leave it like that, so I have to multiply by rad 6 over rad 6. The top is 5 rad 6. There's a rad, but it's okay because it's in the numerator, and the bottom is 6. Okay, one more. 6 over rad 8. I multiply the top and the bottom by rad 8. I get 6 rad 8 on the top. I get 8 on the bottom. However, in this case, I need to simplify a little further because 6 and 8 does reduce to 3 over 4. And I just noticed something. Rad 8, that can be simplified as well. We can't just leave a rad 8 sitting there because rad 8 is rad 4 times rad 2. And we know what rad 4 is, that's just 2. So this becomes 3 times 2 times rad 2 all over 4. And I can do even more. I can cancel the 2 and this 4, leaving a 2. And finally, I get 3 rad 2 over 2. Okay, and I probably give you one that has variables in as well. Okay. Okay, first what I'm going to do for this one is cancel. I know that I could put all this stuff in one rad, so I might as well just cancel. The 15 and the 10, if I divide by 5, gives me 3 and 2. So I know I have rad 3 in the top. X here, x squared down here, so I know I will have an x in the bottom. Y up here, y cubed down here, so y squared down here. Oh, I forgot the 2. There's 2. And I have a 3 out here. Okay, I'm going to leave that 3 for the moment. I'm going to leave this 3. In here, the 2 doesn't have a partner, so 2 is not going to come out. X is not going to come out. The y squared, we know what that is. That's a y. So y comes out. Okay, I have now simplified the individual rads as much as I can. Now I work on the denominator because I have a rad in the denominator, which I'm not allowed to have. So I multiply the top and the bottom by rad 2x. So my top becomes rad of 6x. My bottom becomes 3y times 2x. And I can multiply the 3 and the 2. 6 x, y. Okay, this is fully simplified. Nothing can come out of the rad, so there's nothing to do there. And I don't have any more rads in the denominator, so I know I'm done. Okay, so that's rationalizing denominators.